Okay, so today we'll be talking about something. Okay, it is about quantum mechanics, of course. So let me make it more dense. So, is that too dense? Okay, now, yeah, this is perfect. Quantum mechanics. Now, let's talk about quantum mechanics in terms of uh, waves. Okay, so when we talk about waves, because when in the end we will come to waves as in the form of superposition. Okay, because what I have seen is that whenever the topic quantum mechanics is taught or quantum physics is taught, what I observed is that these two topics, superposition, before this, standing wave, and the starting topic, waves. This is how it's set up. After going through these topics, then actually comes the real topic, which is quantum mechanics or quantum physics. Okay, then they talk about the duality of light, energy levels, and photoelectric effect. After going through these topics, okay, now let's talk about waves. In waves we'll talk about the properties of waves. Okay, these three topics won't take too much long if I just go to overview them, as I won't cover most of like fully. Sorry. Now, now then, this whole thing over here is a wave. We call this whole a wave, a lambda. Okay. Again, lambda is what? Lambda. And what is lambda? Lambda is nothing but the Greek name of wavelength, which is measured in meters. Same as displacement. Okay. And actually lambda is one crust and one trough. These two together make a lambda. Sorry, sorry. Trough. Okay. Now then, after that, then the other property of wave is this over here, and it's very common. It's taught from like grade A7 or A6, which is known as amplitude. Okay, this is called amplitude. Let me write its Greek symbol, amplitude. Okay, now this amplitude over here is actually defined as the displacement gained when there's a disturbance in the wave. Okay, because what we see is a this is a line, right? This is how a string is. Okay, let's imagine we have seen the harmonics. Okay, and on those, this is a string, but the moment we vibrate it up and down, this string changes its shape, right? It gets trough and crust, and that trough and crust is nothing but the amplitude, the change in displacement. And then uh, after that we have, this is a node 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 the ends of the waves, and these are the, the points which were affected are antinodes. Even though we won't be talking about them in detail, but we should just know the details of these. Okay, and Then what else we have is the yeah, two main things again: T, which is period, and F, which is frequency. Okay. Now, period is, which is in T, is nothing but uh, time over cycle, time per cycle, time taken for or a time per cycle, and how much time one cycle has passed, which is one wave. And frequency is the opposite of time and over cycle, which is cycle over time. Okay, so this is all about waves. Yeah, one more thing. This is the equation used to measure the velocity of the wave. This over here is lambda, this over here is frequency. By the way, in wait, we'll talk about it later on. But yeah, till now, till here is all about waves. Okay, then we talk about standing waves. Standing waves. In standing waves, the interesting part here is that we will continue the topic waves, but there's only one difference we will add. Okay, now first of all, what is standing waves? The definition of standing wave is that those waves which have the same phase, speed are equal. Okay, so now this is how it's just the standing wave is actually. Okay, actually, again, this is the I'll just get the overview of these, and these. What are these? Antinodes, nodes, and so on. Nodes as well. Okay, now this is what the standing wave is looks like. Actually, this is the second harmonic. Second harmonic. Okay. Actually, waves come in terms of harmonics. First harmonic, second harmonic, third harmonic, and so on, etc. So this is a second harmonic, and its second name is first overtone. First overtone, and this first overtone is actually, if I want to write in terms of lambda, a lambda equals length over. This is what lambda equals, right? A lambda is this, or a lambda is actually, this is what lambda is, L. Okay, so if a lambda of 1, this is the general formula of lambda, which is lambda n in terms of n is 2L over n, and where n is equals to 1, 2, 3, and so on. When we talk, it's about harmonics. The more we have, the further we go. Let's suppose what we're talking about, this over here. If this is the second over here, this equation of this wave over here is actually of uh, L. It's L, okay? In terms of harmonics, or in terms of wavelength, it's L, okay? So if I put this equation over here, this 2 over here, what do I get? L as well, because 2 cancel each other. So this means this is the general form of this equation is, this is a general form of general general sorry general equation to find the oscillators. Sorry, not oscillator, harmonics. Okay. Now, standing waves. First of all, if someone asks me how standing waves are created, the condition for standing waves being created are here. You might have noticed this is one wave and this is second wave, right? And so here that's the key. Two waves or waves traveling or covering at certain distance, but the waves are in opposite directions to each other, meaning waves traveling both in opposite direction. Now that's first point. Second point, both, and that's the thing. And sorry, let me write. And the word "and" is very important here. This causes super sorry pose or interfere interfere. Okay. Now yeah. So second point taken, and mostly these 2 points are the main points helps us gain which helps us tell about how to make a standing wave. Waves traveling both in opposite direction, and this causes them to have superpose, hence that superpose causes a standing wave. And now let's when we talk about the uh, when we talk about um, the speed of the standing wave. Now speed of standing waves. Okay, here we have two new quantities, T, not T for 10 period, but it's actually tension. Yes, tension, which is measured in newtons. Second is this new Greek letter, which I am also hearing. No, not I'm not hearing for first time, but in terms of physics, it's my first time hearing about it, which is known as mass per unit length. Okay, that's the literal meaning of this mu, because mu can have many definitions, but in terms of physics this is what it has: mass per unit length, which is measured in kilogram meter second, right? Because meter goes, yeah. So and now speed we are talking about. So the general formula is v is equals to speed. As we're talking about speed, right? Yeah, so we don't need that. Uh, this is the general formula for getting speed of the standing wave. Now we could even expand this. Could expand. Okay. Now that I think about the amount of length we will have for this topic, I will be creating this video in two parts. Okay. So in this part we will cover these three topics: superposition, standing wave, and waves. Then in the second part we will combine these and talk about quantum mechanics, and in proper the topics which will be the fundamental, which will be the things on which these topics are helping us to understand it. I don't know what I said just now. Could expand. Okay, we know that speed has a formula: frequency and lambda. Doesn't matter, lambda, frequency, lambda, same thing. And hence we could write frequency lambda equals to square root of t over mu, right? So I could also write it as, this could also be expanded to as frequency mu, frequency is equals to 1 over lambda square root of 1 over mu, right? And let's take this as the general formula for frequency. Okay, now let's talk about when we talk about this as well. Okay, we have, let's suppose we take this as a general formula for frequency in terms of mu. Like, what I'm trying to say is that uh, we could talk about the amount of harmonics, with what harmonic we are on, and this formula will be defining that. So if I give an example of, let's suppose f is equals to 1 over lambda square root of t over mu, and we talk about we talk about how do it, yeah, as let's talk about which one is better, second harmonic, because that is what will give us the proper second harmonic. Okay, second harmonic. Now in second harmonic, lambda is what, 2l, right? No, sorry. In second harmonic it's l. Okay, since in second harmonic it's l, as we have the, let's do a proper way of doing it. Let's do a proper like derivation. We have this equation. Okay, since we're talking about second harmonic, for n equals to 2, lambda 2 is equals to 2l over 2, which gives us l. Since this is our first form of, for we got l now, now we will write our form for this equation, and we could write t over mu. We will write it, and something's wrong here. Okay, so 1 over l square root of t over mu is f. Okay, so if this is the second one, okay, so if this is a second form of that one, and so wait, what was the equation we made over here? 1 over lambda, and this is 1 over lambda as well. This is for second harmonic, right? If we do it for the first harmonic, what do we get? Which is lambda n equals to 2l over 1, 4, n is equals to 1, and so that means lambda n is equals to 2l, and then frequency is equals to 1 over 2l square root of t over u, and so this becomes a general formula, as this over here is So this is what our equation will look like. And then, since this is a first form, because over here what I'm trying to see here is that this equation over here, this lambda over here, is, since this f over v is specified for first harmonic, okay, because this one over here shows for only first harmonic. So I think I could write this equation as this, and since this is for second harmonic, I will write it as 2 mu. Okay, so this is how it will work. And well, it's not necessary to write it like this, but it will give us like a good overview of how to find the change in frequency in terms of harmonics. Now, uh, yeah, so and then what else do we have here? Lambda. What else? Is there anything else I'm missing that I didn't talk about? I should talk about it. Yeah, about the phase of the standing waves. Remember that the phase should be the same. Phase should be same, and speed should be same. And one more thing, important thing. Not every frequency has a standing wave. Okay, so keep that in mind. Okay, so this was the about standing waves, and I hope I didn't miss anything. Now let's come to my favorite topic, superposition of waves. That's not in depth of quantum mechanics, but in next video we'll talk about how superposition works in quantum mechanics. But in waves it's also superposition, similar superposition. Okay, now then, superposition is actually it's actually in terms of being existing in superposition. In terms of, I think I have to go for quantum mechanics, like, to explain this process, but I won't fully explain this. But let's suppose existing in more than one place or coordinates. Let's be a little scientific. Coordinates mean x, y, and z, and time. All time will be same at the same time. So this is what I my way of saying about superposition is. Okay, my way of defining. It's up to you if you want to take this understanding as or not, but I'm like, this is how I find it. Defining. Okay, my way of defining superposition. Now then, in waves, how do oh god, wait. In waves, wave. Okay, so let's suppose this is a wave. Okay, this is one wave plus this is second wave. Okay, they both will undergo interference. Okay, interference, and the moment they're going to interfere in superposition, we will have one more. We will have topics like coherent wave. Sorry, not coherent wave. Constructive waves. Constructive constructive waves and destructive waves. Okay, then wait, what had I just remembered about coherent waves? Well, it's just a definition, so we don't have to worry about it. So, what else do we have here? Yeah, interference pattern. So, here, this is an example. Actually, this is an example of super constructive wave. Okay, constructive wave, constructive wave. Okay, so when we get the result of a constructive wave, actually what we find is that the amplitude change, there's a sudden amplitude change, and that amplitude changes a lot. The amplitudes, this is amplitude, let's suppose is A, and this is also A. In the end, they both combine and become 2A. Okay, so this is how constructive waves are. Why? Okay, wait. Why add? Right, that's the biggest question, right? So why add is because same amplitude. Okay, and then same phase. Okay, and yeah, and on the other hand, when we talk about destructive waves, what was that just now? Did I change my accent just now? Destructive waves. And destructive waves are plus, now not scale, let's provide not to scale. Okay, then Abdullah, so then what we say is as a destructive wave we'll get a flat line. This is a flat line, flat line as now line. So because their wavelengths are now, they were not in, they were no no same amplitude, no same phase. Main points are these, because one of the condition for a superposition is that the waves must be in same phase. And for phase is actually a certain point of a wave of, like, suppose over here, sorry, when we talk about this wave over here, a certain point of the wave at which it is at an angle, it is at an angle, certain angle to the displacement. Okay, so like over here it's 90-degree angle, over here it's a certain angle, but it's taken in terms of. And now how do we compare a wave? We compare a wave with a circle. So this over here right now, this point over here is at this much of the lambda, and this of course over here, which is this part over here. Okay, this is at 90 degree, which is pi over 2. And the way and the uh, to measure the waves, the degrees of wave, the angles of the phase is measured in two types of unit. Okay, phase has two units, which is degree and radian. And then coming back to our topic, no, I mean current learning phase. no same phase, no amplitude, and then superposition. It's a destructive superposition, right? That I already told. It's a destructive one. And what else? What else? What else? What else? What else? Uh, Superposition. Okay, so one more thing: the definition of superposition is existing in more than one place or coordinates. That's okay. This example over here is in terms of quantum mechanics. Okay, not in terms of waves. Quantum mechanics. But in terms of waves, what superposition actually is that, let me see, how do I say this? So what I could say is that, yeah, it is one of a principle, yes, of course, describes how two or more waves interact when they meet. So yeah, the waves, there's an interaction of waves. We have one wave, here we have second wave, and when they combine, the amplitude, the resultant amplitude, the change in resultant amplitude is observed. Sometimes it's positive observation of amplitude, sometimes it's negative observation of amplitude, in terms of you get nothing. This is known as the principle of superposition. It can lead to many different types of interaction, and it leads these are super destructive waves, which is destructive interaction and constructive interaction. And in constructive interaction, both have the same trough or crust, both are in the same phase. And in destructive, the both trough or crust, they must be in opposite um phase, like phase, or yeah. And the example could be that for constructive are two waves of the same frequency in same, okay, yeah, then same frequency mean one other point is same frequency. Okay, no, I wrote hertz as I don't want to write frequency fully. One interesting fact: the destructive interference, they are non noise cancelling headphones. Meaning, okay, now how do we illustrate noise cancelling headphones? That means this is wave one, this is wave one, and this is wave two, right? So how could we illustrate in terms of head headphones? Okay, that's a very interesting thing I just like noticed. Even headphones, those which through which noise cannot go through, but then not 100% uh not 100% of the noise is cancelled. Okay, so we could say that those waves which come from outside are outside waves are actually hit by the same frequency waves inside the headphones, causing them to have destructive interference and have zero amplitude. And zero amplitude mean zero. No amplitude means no loudness. Okay, and one more mathematical representation, which is for high level classes, not for common, is that in terms of, how do I say, in terms of high level mathematics, they could be written as a1 sine of kw minus wt, where w is omega, and when the y2 is equal to a2 sine kx minus wt plus space. Okay, this is just for mathematical, this is just for knowledge. No need to like go into depth on how it is, because just for older grades. And then since these are for different two different waves, the resultant will be the resultant wave, which is y, is actually y1 plus y2, meaning uh, a1 plus a2, sorry, a2 cos theta sine of kw, sorry, minus wt plus okay, a2 as sine of, not theta, this is not theta, this is phi, this is f phi, and this one is of, this one's psi. There's a huge difference. Okay, sine cos kx minus wt. This is the equation of superposition for the waves. And yeah, that's it. This is the first part of the video of on how what actually is superposition and how it works. Like, not superposition, the overview of three topics: waves, standing waves, and superposition. And then we'll tomorrow, or when our next in the next video, we'll talk about superposition in detail, about in terms of quantum mechanics. We'll use this knowledge as well. So thank you.